Alerts went out today about sewage overflows in the Connecticut River. This after another night of heavy rainfall. New 48-hour stay out of the water warnings are now in place in portions of Hampden County.
Where it wasn't just what was coming down that was a problem today, it was what was coming up from the overflowing sewage.
The city of Isleton confirmed with CBS 13 that its sewage treatment ponds have overflowed into the surrounding McCollum, San Joaquin, and Sacramento rivers.
To help prevent homes and businesses from backing up, MMSD started a combined sewage overflow. Public Information Manager Bill Graffin says when the deep tunnel fills up, a relief valve sends untreated water and raw sewage to rivers that then flow into Lake Michigan.
The Mississippi River is a 2,340-mile-long river that is the habitat for more than 100 various species of freshwater fish and more than 400 different species of wildlife, and that also has a long-standing history as a source of drinking water and transportation. Here, where the Mississippi runs through the Twin Cities, it provides drinking water for more than 2.5 million Minnesotan residents, which is 44% of the population. The river is also often used for agricultural, industrial, and recreational purposes. However, the water quality of the river has majorly declined through the decades due to storm and wastewater management problems, introduction of invasive species, contamination from farmland and residential areas, and poor erosion control.
Throughout the 1900s, one of the most important of these factors was combined sewage systems, or CSSs. Combined sewer systems are sewer systems in which untreated residential and industrial sewage and stormwater runoff are collected into the same pipe and sent to wastewater treatment facilities. However, as urbanization became increasingly prevalent during this time, the amount of sewage increased, and during instances of heavy precipitation or snowmelt, the pipes reached their capacity, causing combined sewer overflows, in which the overflow in the pipe flows untreated into a waterway.
In the case of the Twin Cities, this waterway was the Mississippi River. Such instances polluted the river with contaminants and sludge from the stormwater and the untreated sewage, majorly impacting the water quality. This quickly turned into a public health concern, with aquatic life drastically decreasing. In response, in 1933, the Twin Cities developed the sanitary district, and in 1938, they established Pig Eyes Sewage Treatment Plant, treating wastewater with chlorination before dumping it into the Mississippi River. From 1930 to 1950, the quality of water within the Mississippi River improved. However, by 1955, the population of the Twin Cities dramatically increased, and the amount of sewage being handled at such facilities was simply not enough to accommodate the amount of sewage being produced, meaning more raw sewage and stormwater runoff was dumped into the river. Despite such efforts to develop more treatment plants to respond to declining water quality, due to the prevalence of the combined sewage systems, during large precipitation events, CSO events still occurred, polluting the Mississippi River. It was not until 1960 that the Twin Cities attempted to directly address this issue, and the separation of the sewage system and stormwater pipes began.
These CSO events had major effects on the quality of the water in the Mississippi River because untreated sewage combined with stormwater runoff and was dropped directly into rivers and streams. Combined sewage overflows contained untreated human waste, industrial waste, and stormwater, which all have potential contaminants that can damage water quality.
Some of these contaminants include surfactants, which decrease the surface tension of the water and cause foaming. Another type of contaminant is fecal coliform, which reduces dissolved oxygen levels, endangers aquatic animal life, and indicates the presence of disease-carrying pathogens. In a 1950 to 1970 study, surfactant concentrations in the Mississippi River were over 0.5 milligrams per liter, a concentration which can cause chronic toxicity in aquatic organisms. And in a study between 1925 and 1926, it was found that the Mississippi had fecal coliform concentrations of over 100,000 organisms per milliliter. Other bacterial contaminants, such as E. coli, viruses, protozoa, and even pharmaceuticals, can be found in CSOs and cause adverse human health effects as well, such as hepatitis, gastroenteritis, and skin, ear, and respiratory infections. A 1986 study found caffeine levels between 20 to 300 micrograms per liter, which mobilizes toxic metals from sediments and stimulates algae growth. All of these pollutants contributed to the deterioration of the water quality in the Mississippi River and endangered the people of Minneapolis who relied on the river for drinking water, as well as the many organisms that reside there.
We are standing outside of the Twin Cities Lock and Dam.
This dam was created in 1917 by the U.S. Army Corps of Engineers. After its construction, the water became more stagnant above the dam, which caused the concentration of contaminants to become much higher. The contamination was so bad, the U.S. Department of Health had to warn people and their livestock to stay away from the river. As the river was full of sludge, there was a smell, and it was discolored.
This prompted the creation of the Minnesota Sanitary Sewer District.
Nevertheless, by 1928, 3 million cubic yards of sludge had been deposited into the river, and the Mississippi River became filled with floating islands of sewage and scum, and typhoid fever outbreaks were common because of contaminated drinking water.
The number of combined sewage overflows increased even further with the urbanization of Minneapolis and St. Paul in the 1960s, as paved surfaces such as sidewalks and roads prevented water from being absorbed into the ground, increasing the amount of stormwater being drained into the sewer system, causing further backups into residential basements and into the streets. The need for change became apparent, and separation was finally started in the Twin Cities.
This is a sample that we took today from the Mississippi River. As you can see, 100 years later, after decades of work to separate the combined sewer systems, the water's now clearer than ever, and the ecosystem has been revived to the state it was at before the 20th century. According to observations made as a part of the St. Paul Sewer Separation Program, many organisms have returned to the area after around 30 years of absence, including bald eagles and pollution-sensitive Hexagenia mayflies. Fish populations have also increased from 3 species to 25. Furthermore, a study completed by the Metropolitan Council Environmental Services and the Environmental Protection Agency indicated that between 1976 and 1996, the concentration of fecal coliforms in the Mississippi River near the Twin Cities decreased by 70%. And the Twin Cities and Minnesota as a whole continue to strive to make water more sustainable for ecosystems, drinking water, and future generations. Through the Metropolitan Council's Citizen-Assisted Monitoring Program, the Priority Lakes Project, the Water Resources Policy Plan, the Master Water Supply Plan, and others. All of these programs work to monitor the quality of water in lakes and rivers throughout the Twin Cities and to monitor the city's use and treatment of this water, building and improving upon the extensive combined sewer system separation process that they completed throughout the second half of the 20th century that resulted in the clearer, healthier water that is seen in the Mississippi River today.
In 1960, utilizing funds from both the federal and state level from the Environmental Protection Agency, the Minnesota Pollution Control Agency, the Metropolitan Waste Control Commission, the state governments of Minnesota and Wisconsin, and the cities of St. Paul and Minneapolis, the Public Works in the Twin Cities initiated the reconstruction of nearly 600 miles of residential streets within Minneapolis and utilized the project to also begin constructing separate stormwater pipes and reconnect the city's sewage and stormwater runoff to these separated pipes, beginning the separation process of more than 4,600 acres of the city served by the combined sewers. Still facing CSO problems due to the increase of pay services in the Twin Cities, however, in May of 1983, the MPCA commenced an advisory group called the State Combined Sewer Overflow Advisory Task Force to tackle the problem head-on. This task force, made up of representatives from federal agencies from both Minnesota and Wisconsin, environmental groups, and local governments along the river, were responsible for addressing the prevalence of CSOs in the Twin Cities and determining the most appropriate solution to prevent another CSO event. The task force had monthly meetings until October of 1985, whereupon they came to the conclusion that CSS separation was the most appropriate and economical solution to subside CSOs, sewage floodings, and sewage backups to improve the water quality of the Mississippi River. Following the task force decision and recommendations, St. Paul established the $172 million comprehensive sewer plan for the city of St. Paul to be completed by 2025, with the goal of eliminating CSO events and sanitary backups, increasing the system's capacity for sanitary sewage, and reducing sewer service charges by the MWCC by eliminating the treatment of stormwater.
During the time this plan was established, however, engineers within St. Paul estimated that approximately 4.6 billion gallons of raw sewage and stormwater runoff had overflowed into the Mississippi River annually from the Twin Cities, with discharges taking place approximately every 3 days. This encouraged the development of an accelerated joint 10-year, $332 million CSO control program for Minneapolis, St. Paul, and South St. Paul. The goal of this plan was to eliminate sewer backups in basements and implement infrastructure improvements. These include street paving, street light installation, tree planting, gas pipe repair, and water service replacement. The plan also minimized traffic congestion and the disruption of utilities while coordinating with neighborhood street paving, utility work, MNDOT's construction programs, and MWCC's CSO and lake overflow projects. Through this program, they were able to install 189.1 miles of storm sewers, install 11.9 miles of sanitary sewers, pay 168 miles of streets, plant 11,000 trees, and disconnect more than 21,900 residential and 6,140 non-residential rain meters, of which led stormwater from gutters and downspouts to the sewer system. This program also worked to eliminate 26 of the 34 CSO areas in Minneapolis by 1996.
The remaining 8, due to their age, were more challenging, both physically and economically, to identify and separate. However, after multiple intensive projects, which consisted of the creation of stormwater ponds, outlets, and storage tunnels to help reduce flow levels in the pipes, these remaining CSOs were separated, helping to close out the process of combined sewer separation in the Twin Cities. Since then, the cities have continued to work to improve sewer processes and structures, and in 2002, a study was completed on the sewers which identified remaining CSO sites and helped the Metropolitan Council in the city of Minneapolis provide guidance to communities which recommended rain leader and area drain disconnection, drainage system improvements, community education program, and stormwater management practices to minimize runoff and pollution in waterways from both public and private property. Because of this work, there has not been a CSO in Minneapolis since 2010, which was not due to a traditional capacity of the issue of the pipes, but rather due to the collapse of a wall in the infrastructure of the pipe. And 8 years later, in August of 2018, the Twin Cities initiated their CSO permit termination. This permit, known as the Joint Federal National Pollutant Discharge Elimination System and State Disposal System, which had initially been issued in 1984 by the MPCA and EPA and reissued in 1986, 1991, and 1997, was a permit developed under the Clean Water Act with the purpose of acknowledging the existence of the CSO problem and instilling penalties if a CSO occurred in the cities. This permit was supported by the Joint Integrated MS4 permit held by the City of Minneapolis and the Minneapolis Park Board, which is a municipal stormwater permit that focuses on drainage systems from roads, curbs, gutters, ditches, channels, storm drains, and streets, and reducing the entrance of sediments and pollutants into the state waters from stormwater drains. As a part of this termination plan, MCES and Minneapolis and St. Paul specifically defined their responsibilities in regards to connected infrastructure before applying for the joint permit termination, which was then solidified and officially terminated by the MPCA and the EPA.
In an interview with Kyle Colvin, manager of the wastewater planning and community programs at the Metropolitan Council, it was explained that the availability of funding for improvements was the primary driver for the Twin Cities separation process. Colvin explained that in the 1960s and 1970s, there was a lot of federal money available in the form of grants and loans for infrastructure improvements, such as highways and sewers. He said that the local municipalities in Minnesota took advantage of this money to its fullest extent and immediately put it into action, resulting in the separation process previously explained. Colvin further specified the separation process and its benefits, noting how the separation process was the best option for the Twin Cities, because it resulted in the construction of a separate secondary sanitary line right next to the initial CSS pipe that would take in residential and industrial wastewater and direct it to a wastewater treatment plant, leaving the older, larger pipe for stormwater to flow to the Mississippi, increasing stormwater capacity. This was especially important because as urbanization increased throughout the 20th century, so did the amount of impervious pavements of parking lots and sidewalks, increasing the quantity of stormwater runoff. Colvin also explained how the sanitary pipes were newer and tighter, and were made with rubber gasket joints that prevent groundwater from coming into the system, reducing both the loss of groundwater and the inflow of water into the sanitary pipes that does not need to be treated.
The extensive separation of the sewage system in the Twin Cities has for the most part made combined sewage overflows a problem of the past. However, stormwater and sewer problems are far from over, and there are still efforts being made by the Twin Cities to ensure contamination is reduced as much as possible. such as the great deal of integrated work being done throughout the city, which combines improvements such as light rail planning, stormwater tunnel construction, and information of hydraulic and water model layering, to continue to prevent overflows and improve the quality of water within the Mississippi River.
According to Kelly McIntyre, senior professional engineer for the city of Minneapolis, today stormwater runoff and stormwater system capacity are still challenges being addressed through the integrated MS4 National Pollutant Discharge Elimination System permit and through the flood mitigation and storm tunnel programs. Stormwater runoff occurs when rain and snowmelt run over the many hard surfaces in urbanized areas, such as roads, sidewalks, and driveways, and pick up pollutants, such as pesticides or road salts, and enter into storm drains. The storm drains, called MS4 drains, deposit directly into nearby water sources, bringing the pollutants to lakes, rivers, and streams. The MS4 permit for the cities aims to reduce the amount of sediment and other pollutants entering Minnesota waters through the development of a stormwater pollution prevention plan that addresses public education, outreach, and participation, eliminates illicit discharges and construction and post-construction site runoffs, and emphasizes the inspection and maintenance of infrastructure. Minneapolis also implemented the I&I mitigation plan in 2018 to reduce inflow and infiltration in the sewage system through rehabilitation and repair projects. Inflow is when stormwater enters the sewers through roof drain downspouts, foundation drains, storm drain cross connections, and through holes in manhole covers, while infiltration is when groundwater enters into sewer pipes through holes, cracks, joint failures, and faulty connections. In either case, clean water gets sent to treatment plants, lowering the capacity for wastewater in the sanitary sewage system and wasting money on its treatment. One of the main sources of inflow is rain leader violations, which is when the rain leader is connected to the sanitary sewage system instead of the stormwater drainage system, causing combined sewage overflow. Currently, 7,331 out of 7,560 rain leader violations have been resolved. A sanitary tunnel and sewer rehab program is also in place to repair aging or damaged sewer infrastructure. And the cities are working with communities to set personalized limits for inflow and infiltration, to invest in I&I mitigation on private and public properties, and to report violations to the MPCA so that they can find property owners and further encourage them to address the issue. According to McIntyre, another way in which the Metropolitan Council of Minneapolis is trying to address inflow and infiltration is through their I&I surcharge program, which focuses on reducing peak flows from I&I that would require the MCES to construct additional capacity, by billing communities an additional wastewater charge if they exceed the max levels of I&I that are set by the Metropolitan Council Environmental Services. McIntyre also explained how the Metropolitan Council and the City of Minneapolis are working on a 5-year joint capacity study of the regional wastewater system within Minneapolis, which focuses on identifying areas that are at high risk for I&I, sanitary sewer overflow, limited hydraulic capacity, and limited storm sewer system capacity, and working to reduce contributors into maximum storage capacity while developing cost-effective solutions that reduce the risk of sanitary sewer overflow. Despite these improvements, McIntyre and her colleague, Walter Atkins, another engineer for MCES, identified that there are still improvements that need to be made, particularly related to private property. Without financial assistance to private property owners, the city has experienced difficulties trying to decrease I&I on private properties, unlike municipalities which have continuously worked on public infrastructure as it has aged. I&I was also brought up in the Metropolitan Council's Climate Action Plan, as they are trying to evaluate the impacts of climate change on inflow and infiltration to the regional wastewater collection system and develop recommendations to respond accordingly, as climate change has resulted in an increased number of heavy precipitation events that cause the groundwater table to rise, increasing infiltration into the system, reducing its capacity. Due to the Twin Cities' continued work, I&I flow has decreased by 2% since 2005, even as annual precipitation increased by 21% and the Twin Cities experienced substantial population growth. Another prominent example of continued sewer and I&I improvement and mitigation is the SW005 Combined Sewer Overflow Improvements Project. Started on January 1st, 2022, the project is expected to end on December 31st, 2027, after removing the direct inflow of stormwater to the sanitary sewer system and redirecting it to the storm drain system where necessary. This project will reduce the amount of clean water in the sanitary sewer system and lower the risk of overflow.
Right now, we are outside of a construction site that is part of the SW005 project. Right now, they are building an extra stormwater pipe to account for the increased amount of stormwater runoff due to increased impervious surfaces.
Despite these continued concerns, as mentioned previously, sewer separation in the Twin Cities marked a turning point in the water quality of the Mississippi River in the area. This makes the Twin Cities an excellent model of how a metropolitan area efficiently tackled this long-established environmental problem.
Currently, in the U.S., it is estimated that more than 700 municipalities, such as Chicago, Milwaukee, Cincinnati, Boston, New York City, St. Louis, Kansas City, and others, still have combined sewer systems, most of which still experience frequent combined sewer overflows that spill anywhere from 1 to 14 billion gallons of sewage and stormwater overflow per year. Technologies and plans exist throughout the country to try to remediate these issues. One such example is the Metropolitan Water Reclamation District of Greater Chicago's Tunnel and Reservoir Plan, or TARP, which works to collect highly polluted sewer flow that exceeds the capacity of the sewers during wet weather and store it until it can be pushed back into treatment facilities, providing an additional 6.5 billion gallons of storage for intercepting sewage water. A similar example is that of Milwaukee's deep tunnel system, which stores excess wastewater from CSSs underground in a 28.5-mile-long tunnel until wastewater treatment plants can handle the flow. Furthermore, in Cincinnati, the Metropolitan Sewer District is working on a plan called Liquid Run Watershed Strategic Integration Plan as a part of a larger plan called Project Groundwork, which would focus on reducing stormwater entering the combined sewers by building new storm sewers, restoring streams, forming new stormwater detention basins, creating bioinfiltration gardens and bioswales, and daylighting 3 streams that will be able to take up runoff.
However, while these projects are important landmarks in these metropolitan areas' work towards eliminating CSOs, they still do not fully bridge the gap. Despite Chicago's TARP plan, since the beginning of 2021, Chicago has still experienced 138 CSOs, ranging from 30 seconds of overflow to 19 hours of overflow. Similarly, although Milwaukee's deep tunnel system has cut CSOs by 96%, they still frequently have to open the gates for overflow, such as their most recent event between February 27th and March 1st of this year, releasing 230 million gallons of water. Cincinnati also still experiences overflows and will even after Project Groundwork is complete. As one of the top 5 cities in the United States for CSOs, Cincinnati experiences 14 billion gallons of overflow per year, and though Project Groundwork strove to cut at least 2 billion gallons of CSOs by 2018, that still leaves 12 billion gallons unaccounted for. Furthermore, many of these plans and technologies used by other metropolitan districts only provide temporary solutions, as CSO's storage facilities, such as Chicago's TARP plan and Milwaukee's deep tunnel system, have limited capacity and run the risk of becoming septic, corrosive, toxic, and flammable if the wastewater is held underground too long during events of high precipitation and snowmelt. Furthermore, Cincinnati's plan, although focuses on green infrastructure solutions that increase permeability and build watersheds, still have limited effects as well and require extremely widespread use based upon real-time monitoring in order to specifically target the capacity needs of specific areas.
With this in mind, the methodology that the Twin Cities used provides a solid example for other metropolitan areas of how to go about the process of addressing CSOs. Their example provides a clear action plan to go from experiencing CSOs to officially terminating their CSO permit with the EPA, and metropolitan areas can mirror it by following these steps. Step 1. Conduct studies and research to survey the levels of pollution and contaminants in waterways due to CSOs. Step 2. Work with federal, state, and city governments, environmental organizations, and local communities to determine the best plan for going about CSS separation. Step 3. Form a task force consisting of people from major organizations of interest to address CSOs directly. These organizations of interest could be federal agencies, state governments, local government representatives, environmental groups, etc. Step 4. Identify funding sources. These can include federal grants, financing partnerships, pay-as-you-go programs, or joint federal, state, city funding. Step 5. Consult and contract construction companies. Step 6. Develop a comprehensive sewer plan. This plan would identify key areas of construction, funding sources, and community engagement. Step 7. Execute plan. Step 8. finish sewer separation, and identify and make plans for future improvements to address further issues. Just because the CSO issue is taken care of does not mean that there is still not work to be done. Inflow and infiltration and stormwater runoff are still major issues that must be addressed even after CSOs are handled, meaning that a long-term plan should be developed to identify and improve these issues. Step 9. Coordinate with and educate communities about how they can work to remediate stormwater and wastewater issues locally. This can be through classes for homeowners, rebates, PSAs, or other programs. Step 10. Officially terminate the city's CSO permit with the EPA, declaring that they no longer experience CSOs. Through this Twin Cities action plan, other metropolitan areas can go about the process of CSS separation and officially end CSO events.
Despite high upfront costs for separation and continued concerns regarding stormwater and runoff pollution, as a result of their in-depth methodology and the complete separation process, the Twin Cities has not experienced a CSO event since 2010, which occurred not because the tunnel's hydrologic capacity was reached, but rather because the tunnel's infrastructure itself failed. Every metropolitan area across the U.S. can utilize the Twin Cities as the prime precedent of not only how CSOs can be addressed, but how a long-standing environmental issue can be tackled efficiently to begin providing a brighter future for both our communities and our environment.